Welcome everyone, people here in person, and I hear there's a very large audience online as well. Welcome to this very special lecture by Professor M.S. Raghunathan on an overview of the historic Atiyah Singer index theorem. Sometime back, Professor Raghunathan wrote saying he would like to give some talks on a new proof of the Atiyah Singer theorem that he has been developing. And it was, so I jumped at the opportunity, and I made a special request to him that, of course, we will have the technical talks, but we would very much like to hear his broader perspective, and also to kind of, for the general members of ICTS and others, to have the larger context in which this theorem sort of sits. Since it is one of the very important foundational results of 20th century mathematics, and indeed has had a great influence even in theoretical physics, not only in high energy physics and condensed matter physics in many areas. It was very kind and generous of him to agree to prepare such a broad talk as well for this, for a broader audience. And he will also give us the series of technical lectures building on this. And so for those of you who would like to see a proof of the theorem, this will be developed over the following 3 lectures or so by Professor Raghunathan. I think the next lecture is on Monday at 10:30 a.m. These will also be broadcast over Zoom. And I think, I said Monday, okay, Wednesday, sorry, Wednesday day after tomorrow at 10:30 a.m. And then the following Monday, and I think Wednesday after that. That's right, over the 3 lectures. These will also be broadcast over Zoom, and the link will be available. So please join in. I would, of course, it's a bit superfluous to introduce Professor Raghunathan, but as many of you know, he is one of the celebrated mathematicians from India whose work has had a global impact with fundamental contributions in the, to the structure and cohomology of discrete subgroups of Lie groups, and which has shaped the subject. In particular, he settled a famous conjecture of Selberg on the arithmeticity of certain higher Q-rank lattices in semisimple Lie groups, and results on the congruent subgroup problem. One of his very famous conjectures on the relationship between ergodic theory and the Oppenheim conjecture in number theory spurred a lot of research and results, which was eventually settled by Margulis, the Fields medalist. Professor Raghunathan has not only had multiple impactful contributions in mathematics, but he has also been very much involved in the development of mathematics in India at various levels. I mean, both in the School of Mathematics at TIFR, now through the NCM in IIT Mumbai, but also through the, for many years, his involvement even continuing with the National Board for Higher Mathematics, NBHM, the entity which sort of has helped to sustain mathematics across the country in many ways, starting from the Olympiad level, and you may have all heard of the remarkable performance by Indian school children this year. These are some of the ways in which NBHM has impacted Indian mathematics, and Professor Raghunathan has been very key in that. It was also his brainchild to bring the International Congress of Mathematicians, the ICM, the flagship conference in mathematics, once in 4 years, which was held in Hyderabad in 2012, I think. So that was, again, organizing such a massive enterprise also speaks to his other skills. In terms of his impact in mathematics, also through his students. Some of his students are very eminent mathematicians in their own right, like Professor Gopal Prasad, S.G. Dani, Professor Dani, and Professor Vinay Diodhar, and so on. So anyway, I will not go on, and we will hand it over now to Professor Raghunathan. I should only add that I think this is Professor Raghunathan is returning to a kind of early love of his on topology and geometry, or probably an abiding one, returning to the Atiyah Singer index theorem. Thank you very much, and please.
Thank you, Rajesh, for your introduction. I'm afraid I'm not too sure that I will live up to what he expects of me from this lecture. I'm going to say some things about the Atiyah Singer index theorem. As he said, I have a slightly different proof from the original proof, and also very different from all the proofs given by Patodi. Atiyah bought Patodi, and Patodi himself series, and then there are proofs by other people. Bismuth has a proof which uses probability techniques, which I know nothing about really. And there is this Michel Verne. Michel Verne has a proof using the Dirac operators, whereas Gilkey also has a proof using it. Gilkey's proof is really both Gilkey and Michel Verne. Their proofs are takeoffs on Patodi's method. They simplify the various calculations that Patodi did using some invariant theory. I have some acquaintance with those proofs, but I'm not I don't have a really deep knowledge of that. Anyway, I'll say something about those things. I devised a proof. I shouldn't say it's not an entirely new proof. It's based on what the outlines is the same as that of the original proof Atiyah Singer, but there are several points where it is much simplified. That's the kind of proof, and I'll talk about it today. I do not know. It's a little difficult to cater to an audience without the kind of background in differential geometry, topology, and differential equations to convey what exactly this theorem is all about. And nevertheless, I'll try something, and if I fail, I would not be surprised, but I hope you will not be disappointed. See, preparing the slides has been a difficult job for me. It's never easy to do these things, but I've done something, and in fact, after the slides end, I still have something more to say, because I couldn't put them in the slides. I didn't have the time to do it. So I'll say something on the board, with which I'll be much more comfortable. The Atiyah Singer theorem is certainly one of the great theorems of the 20th century. It's a theorem. It was proved in 1963. So it's now 62 years old. So 61 years old. In fact, at the time when it was 50 years old, I wrote to Atiyah, inviting him to come to India and give some talks on the Atiyah Singer index theorem, celebrating its golden jubilee. He agreed readily, and I was very happy. But a few months later, he wrote to me saying that he can't come because his wife doesn't want him to travel. So that was the end of it. I mean, I had a fascination for this theorem ever since it came on the scene. My first introduction was in a seminar which Narasimhan and Ramanan had organized at TIFR, in which I also participated, and I lectured a good deal in that course, and where we fixed up all the proofs. We saw the announcement. We didn't have the proofs cleared up, but we had the announcement, and we had sort of worked out the proofs more or less completely in that seminar. But in that seminar, we followed verbatim everything that was said in the Atiyah Singer announcement, and Later, of course, there is a seminar on the Atiyah Singer index theorem conducted by Palais, where all the details are given. And we didn't really cover all the details there because we were not familiar with them, and it went a lot of hard work to get to understand what was going on. But we had a broad idea of what was going on, and with some hand waving, we did give a complete proof of the theorem in that seminar. Anyway, that but actually some years later, about how many years now? 15 years back, there was a conference in honor of Ramanan's 70th birthday in Spain. And I was wondering what I was asked to give a talk there, and I was wondering what I should talk about. And then in a bout of nostalgia, I thought about the seminar we had. And thinking about it, I arrived at somewhat different proofs, pleasanter, easier proofs than the original Atiyah Singer proof. And I wrote it up as a paper, and it appeared in that volume, in the Ramanan's 70th birthday volume. It has appeared. And what I'm going to talk about will be based on that paper. Though it's 15 years old, not many people know about it. It's not known. I sent the paper to Atiyah. Atiyah, by that time, had kind of lost interest in the business, and so he didn't really respond. And I persisted and wrote to him again, saying that I sent the paper, I hope you received it. And he said, yes, I received it, and it's a good idea to dedicate the paper to Ramanan's birthday. That's all he would say. Anyway, that's the background story. So it's a theorem which really fascinated the entire mathematical community, and it's at the interface of different areas of mathematics, making deep use of results from those areas. So I will essentially describe the theorem and make some historical remarks. Actually, the historical remarks will not come in the slides. They will come after the slides because I didn't have time to put them in the slide. I was working on the slides till about an hour ago. So I will spend some time to say the background information, to give the background information necessary. It was necessarily be sketchy and somewhat vague. Some hand waving is inevitable. I expect that the audience have some similarity all the same with these areas, even if they do not work in the relevant area. This theorem is about elliptic differential operators on a compact manifold from one vector bundle to another. I'm going to tell you what an elliptic operator from a vector bundle to another is. To define this notion, we need the concept of a vector bundle, which most of you will be familiar with. Nevertheless, I'll go through the motions of making a definition. So F will be real numbers or complex numbers. I'll be talking about complex or real vector bundles. Most of the time, it will be about complex vector bundle, but real vector bundles will inevitably figure. So I'll define a vector bundle. It's a pair consisting of a topological space E and a projection map PE to X, consisting of a topological space and a continuous map PE satisfying the following conditions. First condition, for every X in X, there is given a vector space structure on EX, the fiber. There was space X here and bigger space here, and a map down here. Each point on each of these, this is a vector space structure. On pi inverse X for every X. that's given and then there's a local triviality condition. For every X in X, there's an open neighborhood U over which this space will look like just a product. And I spelled it out in precise terms. For every X in X, there's an open set U in X with X in U. This U here opens. There's a mapping from U cross this vector space of some rank R, FR, back into this, the inverse image of this portion. This is U. So the inverse image of this portion. There is a homeomorphism, which on each fiber, on this fiber, there's the vector space structure. Simply it's FR. Each FR is mapped vector space isomorphically onto the corresponding inverse image fiber. So, and the mapping is compatible. Projection here is same as the projection here when you compose the homeomorphism. That's the definition of vector bundle. When X is a smooth manifold, the base space is X. When X is a smooth manifold, we can talk of a smooth vector bundle, where all maps should become, all objects are going to be manifolds, smooth manifolds, and all mappings smooth, differentiable, C infinity. That's the kind of thing. So the definition of this is such a thing is called a local trivialization. And in that definition, you demand, if it's a smooth vector bundle, you demand this diffeomorphism. Then you call it a smooth vector bundle. From now on, all vector bundles, if I talk of vector bundle on a smooth manifold, I automatically assume it's a smooth vector bundle. For X in M, a smooth manifold, Txm and Tx star M represent the so-called tangent and cotangent space. These are essentially, if you have something you call something a tangent vector, if you look at all curves passing through that point, which touch each other, their common thing is called, whatever is common to them is called the tangent vector. And that forms the vector space, which I call Txm. M is the manifold, X is the point on the manifold. Txm is the tangent space, and its dual is called the cotangent space. The disjoint union Tx star X in M has a structure of a real vector bundle, and it's denoted Tm and T star M respectively. So when you have if you think of a manifold as something sitting inside Euclidean space, you have at every point tangent vectors to that point. These are, of course, you have the tangent plane there or tangent space of some dimension translated to the origin, and then you get vectors of space here. That's how Txm can be identified in the case when the manifold is submanifold of Euclidean space. The usual notion of tangent space, our intuitive notion of tangent space works. And so, as a structure so this union of all the tangent spaces at various points, considered as disjoint, has a structure of a real vector bundle and is denoted Tm. And the corresponding dual is the thing is denoted T star M, and is a tangent or cotangent bundle of M. Ptm Txm equals X. For a vector bundle, you always have a projection, and that projection takes the tangent space at X into X itself. That's the definition of the tangent bundle. Now, next I will talk a little bit about K-theory, which intervenes very decisively in the statement, even in the statement of the Atiyah Singer index theorem. There is a way of getting around that, but you don't have to, technically you can go around without using K-theory, but it's not clear why, if you don't know K-theory, you don't see how it works, that method of doing it. You can use curvature form and do something with it and arrive at it, but without K-theory, it's not clear why that should be the formula, finally, for the index. So, one, of course, has a notion of homomorphisms. I usually use the word morphism, which is more common among mathematicians. A homomorphism and morphism are the same. So, you have the notion of a homomorphism between vector bundles. It's the obvious definition. You have a map of the one vector bundle E into another, which lies above the identity map of the base M, and such that in each fiber the mapping is a vector space homomorphism. And there are obvious definitions of direct sums and tensor products, E tensor E prime and E direct sum E prime of two vector bundles on X. You just have to put together, you have two vector bundles E and F, say, you just have to look at the vector space Ex, X is the fiber over X of E, and Fx is the fiber over X of F. Then you just look at Ex tensor Fx and take the disjoint union of those and make it into a vector bundle like we did in the case of tangent bundle. So that's where tensor product is. Direct sum is also defined similarly. We need these concepts. Now, for the definition of what's called Kx for a topological space X, let Vx be the set of script Vx be the set of isomorphism classes of complex vector bundles on X. For a vector bundle psi, I will use the Greek letter psi for a vector bundle, which will denote which will mean a pair already. So vector bundle psi, and that I forgot to put the right slash before the xi. So that's psi. And its isomorphism class is simply denoted psi. So if psi is a vector bundle, its isomorphism class is square bracket psi. Then one forms AX is the free abelian group on Vx and Bx. And Bx is a subgroup generated by psi, isomorphism class of psi plus isomorphism class of eta, that's in the abelian group, minus the isomorphism class of psi plus psi direction eta, where psi eta are vector bundles. You pass to the quotient of Ax by this subgroup, the Ax by Bx is usually denoted Kx, and that is it's a functor from the category of topological spaces into the category of vector bundles. Sorry, into the category of abelian groups. So for each x, you are associated Kx. Whenever you have a continuous map from x to y, you are mapping from ky to Kx backwards. It's what they call a contravariant functor. The definition of Kx is simply Ax by Bx. If x to y is a continuous map and E prime is a vector bundle on y, the fiber product x cross y over E prime is a vector bundle. Or that is, you have a vector bundle y on E, you have x here, you form the product x cross E, the Cartesian product, and in this you look at so x in x, so this is f here, it's pi E there, and look at all x E in x cross E with the condition that PEV is Fx. This is called the fiber product. Basically, you have this space here, and you have this space here. Over each fiber, each point you have a vector space, and if you take a point x, and here is Fx, you take the vector space over that and plug it in there. That way you build a vector bundle on X. That's called the induced bundle or inverse image bundle under F. And it's denoted F star E prime. The map E prime to F star E prime yields a morphism from Kf to, yields a morphism Kf from Ky to Kx. So the vector bundle level, each vector bundle is pulled back, and then you can you get a mapping from the free abelian group to the free abelian group, and the corresponding kernels the corresponding kernel maps into the kernel, and then the kernel maps into the corresponding kernel, and then you get a mapping of the quotients. So that is Kf from Ky to Kx. Now, and then one defines the K group for a pair Xa, where X is a topological space and a closed subspace. For such a pair, you define Kxa as follows. So it's defined as you look at K x by A point. Let's explain what this means. X by A is a space, you have this X here, and you have a closed subspace here. Blow this down to your point. So this whole thing has become a point here. For instance, if you take an interval, blow down, this is say the endpoints together is A, say. A is this plus this. These two together is A. When you blow down the thing, you get a circle. This is, endpoints are simply mapped into a single thing. That's the kind of thing. But if you take a disk, for instance, D2, and the unit circle, D2 by S1 is nothing but S2. Two sphere. Fold over. That's how the space is X by A is defined. And then one defines a mapping K. What's the definition? You look at K X by A star is defined as, you have a natural map from K X by A star to Kf star. Sorry, you have a natural map from K X by A to Kf star. What is Kf star? Star is a single point in a vector bundle, means simply vector space. This is nothing, and the rank gives you an isomorphism with Z. So you get a mapping of Kxa into Z. The kernel is what is called Kx by A comma point. So, and Kxa is simply defined as K. You blow down A, get a space with a space automatically acquires a point. The whole of A has been blown down to a point. It acquires a point, and so that's the definition of Kx by A. So Kx by A is the kernel of the mapping. Ki, the inclusion I of point in A induces map from, as I said earlier, Ki, Ka to K star, and this is Z. And then you have a map rank E. It's a map from the space Kx to Z. Rank at the point star. Sorry. Okay. Rank star is a mapping from Kx to Kf star when you have a point star to Z. And when the star is something which is there already, I'll forget this rank and simply call it rank. But if you have lots of points, it goes into, it's a function to Z, which is locally constant. So if there's no star, locally constant on X. Because when the definition of vector bundle, if you take a point in the neighborhood, it looks like you cross a fixed vector space. And so the rank is well defined in that entire neighborhood. So every point is a neighborhood in which it is constant, and therefore it's locally constant. So it will be constant on connected components. When X is a point, the map induces the rank map gives you a homomorphism of Kx into Z. Formation of tensor product of vector bundles leads to a ring structure on Kx by A, and the assignment Xa to Kxa is a contravariant functor from the category of pairs Xa, Xa topological to a subset into the category of commutative rings. There's a ring structure on Kxy in general. It comes from formation of tensor product at the vector bundle level. Then you have to, of course, check that you have free group on isomorphism classes, tensor free group on isomorphism classes into free group into the, sorry. The tensor product gives you a mapping from set of isomorphism classes, tensor cross set of isomorphism classes into set of isomorphism classes. F going to E tensor F. And then that gives you a mapping ultimately from Kx tensor Kx to Kx, which is a multiplication. Kx by A tensor Kx by A into Kx by A. So each this Kxa is a ring in a natural way, given by the tensor product. Now there's an important construction which is important from the point of view of the Atiyah Singer index theorem. Suppose you are given two vector bundles and an isomorphism phi of E restricted to A. Restriction to A makes sense because you just take the portion over A. That's the restriction of A. So, and suppose there are given two vector bundles and an isomorphism of E restricted to A on E prime restricted to A. Then one can define an element bracket phi in Kxa as follows. What one does is the following. You have a space X, a subspace A, sorry, A here. You have a vector bundle on this, and another vector bundle also on this. And over the portion A, you have an isomorphism. In such a situation, you can define this data gives an element phi in Kxa. This is usually called the difference element. defined by phi. So you get an element K, and this construction is important in the when you for the index theorem. In fact, in a short while I'll talk about the symbol, the K theoretic symbol, and that depends very much on this construction. Well, I don't want to go much into the construction but very quickly, what one can do is to add by forming direct sum with another bundle F. These are two bundles. This is E here and F here. And what one can do is to it's a theorem that you can find the bundle F prime such that this becomes a product bundle. If you are working on X cross C. And you obviously have a phi direct sum. One will be an isomorphism between E, it will be E restricted to E direct sum F prime restricted to A on F direct sum F prime restricted to A. So, and this is isomorphic to the trivial bundle, so this is nothing but A cross some CQ. And now, in such a situation, what you can do is when you can blow down A and use this isomorphism to identify all the fibers over A on both sides. And therefore, you will get a vector bundle, which is, you get a vector bundle X by A, and with a trivialization on the base point which you get, which is the definition, which gives you the definition of the element KXA. So that's the difference construction.
Guaranteed that you will find such an...
There is always an F prime such that F plus F prime is trivial.
The capital N is not fixed. The capital N, or what you call Q here.
Sorry, here.
You've called it probably Q or capital N.
No,
that is...
Oh, it should have been N. The Q should have been capital N, yeah.
But that capital N is not fixed in terms of the ranks of the original.
Yeah, I mean, the thing is that there's no uniqueness about E double prime.
Okay. It could be anything. It could be.
I mean, for instance, you start with one E double prime, add another trivial
one, and you can.
So that gives an element of KXA, and there's a number of, in the definition, there's a number of choices involved, but the ultimate element in KXA which you get, that bracket phi is independent of the choices involved. You have to choose some E double prime there, it doesn't matter what you choose. Okay, now I come to definition of linear differential operators and their symbols. M is a smooth manifold. One can speak of smooth vector bundles. E is smooth and P is smooth, etc. I've already said all this. We denote by gamma UE the set of all smooth sections of E over U. So a section simply, here is the vector bundle, the manifold here, and you have, suppose you have an open set here. Its sections are mapping in the other direction, such that when you come back with the projection here, you get identity. That is, for each point, you pick a point upstairs, such that which is smooth, the mapping is smooth, and the composition is identity. That's a section. You can obviously add sections. If it's a vector bundle, you can add sections and multiply sections by scalars. So it's a set of sections become a vector space. So a definition is of a linear differential operator L from E to F is a collection LU for every open set U. LU is a linear map, C-linear map from gamma UE to gamma, that should be gamma, not G. Gamma UE is sections over E, gamma UE prime sections over sections of E prime. So gamma UE to gamma UE prime, you have a map LU for every U, such that when you take a section restricted to some open set, you have on the smaller open set you have an LV, and on the bigger open set LU, and that diagram should be commutative. That is, whichever way you go, you get the same map. Whether you go this way or this way, you get the same map. That's what it means to say the diagram is commutative. So such a thing is a linear differential operator. Now, Of course, one may be a little puzzled about this kind of definition, but it turns out that the theorem says that gives us back our idea of a differential operator on Euclidean space without any further assumptions. Here is a following theorem is a result of Jacques Petre, which says that the above definition is not at variance with our ideas about differential equations in Rn. So if you restrict to know sufficiently small open set, then sections of that open set can simply be thought as vector valued functions on that open set, because over that open set the thing is a product. So a section means mapping will go into the fiber, which is a fixed. So there are sections, so vector valued functions on U, and you want from vector valued functions on U, say vector with values in a vector space Rp to another. So you want get functions. The operator gives you a map into functions on the same U, but with values in some Fq, different Fp and Fq. So from vector valued functions to vector valued functions, of the size of the vectors are different. You get a map D, and then it turns out you get back the usual notion of our differential operator in Euclidean space. It's a theorem which is not very difficult to prove, but somewhat technically involved. That theorem is due to Petre. Now, that will happen only on a relatively compact open set. What could happen is you can write, even on Euclidean space, you can write a differential equation, say A alpha x d alpha, and then you can make A alpha, the A alpha x can, the A alpha x can be non-zero for larger and larger alpha as you go to infinity. That kind of thing can happen. In any compact set, it won't happen, but you can increase the degree. I mean, you can write, for instance, one variable, you can write d by dx power n, a and x. These functions a and x can all be functions compact support, but the support may grow as you grow, as n goes larger and larger. So you cannot put a bound on the order of the operator. That's one thing one should keep in mind. If you look at the definition on any relatively compact set, you do get a bound. It gets written as a n d by dxn with a n terminating at some point n. So I've written it out. D alpha means d by dx1, etc. So this operator, after composing with on both sides with suitable functions, suitable isomorphisms, you find that it's the usual linear differential operator on Euclidean space. The differential operator L is of order D if for every coordinate chart you have M with U relatively compact one as du less than equal to D. Fixed D, independent of the relatively compact set if you have, then you call it a differential operator of order less than equal to D, and something is of order equal to D if it's of order less than equal to D but not less than equal to D minus 1. Let L be a linear differential operator of order D. In the coordinate chart, you have fixed the coordinate chart. The dxi, 1 less than to I less than to p, at every point constitutes the basis of the cotangent space at any point of view. Once you have that, then if you look at the map, which sigma ti dxi going to take only the coefficients of the top degree, top order operators. Alpha is d alpha is the composition of d by dx1 for alpha, etc. Alpha 1 plus alpha 2 alpha n is fixed, which I call mod alpha. Fix mod alpha equal to d, and then look at this polynomial in the t1, t2, ti, tp. Actually, this should be the manifold I've always been talking of being dimension n, so that should be n. Never mind. So here it's as if the manifold is a dimension p. I write it like this, then I get this. You get a homogeneous polynomial of degree d on the tangent on this vector space spanned by dxi. You get a matrix valued homogeneous polynomial on the cotangent space dxr at x for every x in u. The trivializations of the bundles enables one to identify the matrices elements of home ex prime. It's easy to see that this homogeneous polynomial is independent of the choice of the chart as a polynomial on the cotangent space. It's independent of the chart. in a different chart, you'll get a different basis, but the polynomial also look different. But when you think of them as the same tangent, cotangent vectors, then you're in good shape. The evaluation gives the same value. So we get in other words, we get a vector bundle morphism of the pullback of V from morphism of the pullback of V to the pullback of V prime under PT star T star M. So for each vector V in the cotangent space, you get an isomorphism of, you get a polynomial map into the homomorphisms Ex into E prime X. So what you get is essentially a morphism of the pullback of E to the pullback of E prime under PT star M. This bundle morphism is called the symbol SLFL. That is, you have this manifold here. This is the tangent bundle, say, cotangent bundle. And you have the other bundles also sitting here. E, F. So what you take a element V in the cotangent bundle, and you have, the symbol gives you V is lying over X, and you get X over X. You have EX here, this is EX, and you have FX here, and you get for each V, you get a homomorphism of EX to VX, which is SV. Depending on V, SV, and the way the SV depends on V is a polynomial dependence. It's a homogeneous polynomial, and that's I called it by boldface S L symbol. Let's call the symbol. Sorry. What is the
symbol
yeah
of the Laplacian?
Laplacian sigma xi square, sigma psi I square. That's it for the Laplacian. Yes. So after all, sigma d square by dx square is Laplacian, and you just to think of this as if I vector like tangent vector like this, I just have psi1 square plus psi2 square, psi square. Norm square is the symbol. The top order terms is the essentially symbol, thought of as a polynomial function on the tangent space, on the cotangent space. Now fix a Riemann metric on M and let dm and sm denote the unit disk and unit sphere bundle. It's clear how to define it. That is, when you have Riemann metric on every of these, one of those tangent spaces or cotangent spaces, you have a inner product. You have a Riemann manifold, and therefore it makes sense to talk of unit vectors in that, or vectors of norm less than or equal to 1 in each of those fibers. And you just take only those of norm less than or equal to 1, you call that the disk bundle, and those of norm exactly equal to 1, you call them the sphere bundle. So at each point you have a sphere and a disk which it bounds. So thus we have two vector bundles, E and E prime, boldface E and boldface M over dm, and a homomorphism S E to E prime, which is an isomorphism over Sm. So think of dm as a space X and Sm as a subspace S A. Then we have two vector bundles on them and a homomorphism which on the subbundle, on the subspace is an isomorphism. So we are ready to make the difference construction, and therefore you will get an element. You get an element sigma L, which depends on the original operator L. The sigma. Yeah, we had a morphism SL, and now which is an isomorphism as far as Sm is concerned. Sigma L in KDM Sm is the k-theoretic symbol, the elliptic operator. Yeah, I forgot to say. The operator is said to be elliptic if the symbol map is an isomorphism on the sphere bundle. So you have on the disk bundle you have mapping, you have a vector bundle on the disk bundle and a homomorphism to another vector bundle, which when you restrict to the sphere bundle is an isomorphism. And that's why the difference construction comes up. And so you get an element of K B disk bundle modulo S sphere bundle K DMSM and sigma L. That is called the symbol of the elliptic operator. It's defined only for elliptic operators. It's not defined for arbitrary operators because we want mapping to be isomorphism on all the non-zero vectors. In particular, if it's going to be, it's a homogeneous polynomial. If it's non-zero on the sphere, it's going to be non-zero on all the non-zero vectors. If it's going to be isomorphism on all the non-zero vectors. And this element is again independent of the choice of the Riemann metric. These are not difficult things to prove, but technical. So the following result is well known. I want to define now the analytic index of an elliptic operator. M be a compact manifold, E prime be vector bundles on L, and L vector bundles on M, and L an elliptic operator from E to E prime. Then dimension kernel LM and dimension co-kernel LM are finite. If you have mapping from one vector space to another, P prime, the kernel is set of elements X in V, Px is 0, and co-kernel by definition is V prime over V, the quotient V prime over TV. Both these are finite when the operator is elliptic. This is a now standard theorem on differential equations. Actually, these terms were proved essentially in the first half of 20th century, not before that. I mean, for one reason, people were not thinking of compact manifolds before that. But anyway, that was that's the theorem. And then that theorem enables us to define the index of an operator. The integer dimension kernel LM minus co-kernel LM. LM is the operator from all sections, global sections of the compact manifold. Dimension kernel LM minus dimension co-kernel LM is the analytic index of IAFL. So this takes all this time to define the analytic index. Okay, and of course, when you have a differential operator, one would very much like to understand what its kernel is like. What are the solutions to the operation? But that is usually intractable problem. You cannot, in general, get hold of that very easily. However, it's easier to get hold of the difference between the dimension of the kernel and the dimension of the co-kernel for a number of reasons. Firstly, it was observed, for instance, that if you vary the differential operator continuously, keeping it elliptic but vary it continuously, then the kernel minus co-kernel, the dimension, does not change. The kernel may change, the co-kernel may change, but if the kernel increases, so does the co-kernel. So the difference remains the same. So, in other words, under perturbations, the index doesn't change, whereas solutions can completely go off the radar. A crucial fact needed in the proof of the index theorem is the following. IAL and IAL prime for elliptic operators, L prime on a compact manifold. Sorry. A crucial fact needed in the proof of the index theorem is these are equal if L and L prime, sigma L and sigma L prime are equal. I seem to have forgotten completely to put that in. That's a crucial statement. If the K-theoretic symbols are the same, the theorem is if sigma L equal to sigma L prime, both are differential operators, elliptic, then analytic index is the same for both. I mean, it is basically suppose you take the symbol of one, symbol of L and symbol of L prime. Suppose you can move them continuously. Then it's really a theorem in functional analysis. Using some inequalities for elliptic operators, if you move through elliptic operators from one to another, but that suggests that this may be true, but this is of course much stronger. It's not clear that just because things move, things are involved in the deformation of the kind I'm speaking about, because during the deformation, first of all, the symbol, all the symbols must have the same homogeneous degree. and they move, then you can prove the kind of statement one wants. But it suggests that there's something much more valid, namely, if the k-theoretic elements are the same, then the analytic indices are the same. Okay, this is a true theorem, and the proof originally given by, yeah.
Can I ask a question?
Sure, sure.
Is there a formula actually for this?
Sorry?
Is there a formula for the index in terms of the...
The index theorem is the formula for the index, analytic index, in terms of some topological invariance.
So that's what I'm asking actually. So
that's the index theorem. The theorem says there's going to be another thing which is defined purely geometrically without any analysis, which turns out to be equal number, which turns out to be equal to this.
So my actually question is more specific actually, that if I know a Dirac operator in the presence of some gauge field, or if I look at a Dirac operator in a Riemannian manifold, I understand this type of thing. But suppose I give you some arbitrary elliptic operator.
No.
Then
there is a geometric way of arriving at another number, which is called the topological index.
Yes.
And I'm going to describe that. Okay. And the theorem is that the topological index is the same as the analytic index. The geometric index does not involve any analysis. Okay. It's all completely geometric in character. I'd already told Rajesh, I don't know if I can complete what I want to say in 60 minutes. Maybe I'll spill over. I planned for 90 minutes, but maybe I won't take 90 minutes, I'll take less. So, to prove that IAL equal to IAL prime for when the k-theoretic symbols are the same is a difficult result. It's not easy. And the device used by Atiyah and Singer is a sophisticated machinery of so-called pseudo-differential operators. What happens is that there are symbols. There are certain operators for which you can, the whole class of operators for which you can define symbols. These symbols are no longer homogeneous polynomials of any particular degree. They are simply continuous functions, or at least smooth. They're simply smooth functions on the disbundled values in the isomorphisms of E to F. That's the kind of stuff you will deal with. And there are corresponding operators which are called pseudo-differential operators. They have symbols, but symbols no longer homogeneous polynomials. They are simply some continuous function, or smooth functions. Instead of being homogeneous polynomials like here on each fiber, they are going to be on each fiber some continuous functions. And once you have symbols, ellipticity is defined a similar way. And once ellipticity is defined, you get an isomorphism purely from a k-theoretic point of view. We don't care whether they are homogeneous polynomials or not. There are some continuous mappings, and so you do get a difference element corresponding to that kind of data. And once you have that kind of data, you can define the k-theoretic symbol, but for pseudo-differential operators. And in pseudo-differential operators, you can do the homotopy in any way you like. You don't have to pass through only homogeneous polynomials. Okay, I mean, you can pass through same polynomials on the sphere. At one end, it may be homogeneity of some kind, at other homogeneity of another kind. But as far as pseudo-differential operators are concerned, you can do that and conclude that the index remains the same. And that flexibility is what enables them to prove what Atiyah and Singer enables them to prove. What enables Atiyah and Singer to prove that the k-theoretic symbol determines the analytic index of a pseudo-differential operator. And pseudo-differential operator is much more flexible, but there's a lot of machinery which goes into it in defining and proving properties of those operators.
But this theorem is not true for pseudo-differential operator.
Which
I mean, the equality, if L and L prime are two arbitrary...
Yeah, it's true for pseudo-differential operators.
If they're k-theoretic...
In fact, they prove the theorem for pseudo-differential operators.
So it's more general.
What I'm going to describe is for differential operators, and it can be extended to pseudo-differential operators by some further work. But what I'm going to talk about is essentially proof in the case of differential operators. Okay.
So that sounds much more powerful. So you're saying this result is true for pseudo-differential operators, but the index theorem will finally be only for differential.
No.
Index theorem is also for
pseudo-differential operators. They prove theorem for pseudo-differential operators. I mean, the reason I confine myself to differential operators, one is that pseudo-differential operators make it much more complicated to explain what they are. It's a very sophisticated business. Okay, and also, also the theorem's main interest in the theorem is for differential operators. Those pseudo-differential operators are interesting in their own right, and they have probably a role in physics as well, but I don't know. But anyway, so but the point is that usually most people are interested only in differential operators, and for that it's enough. And after proving it for differential operators, with a little bit of work, you can also extend it for pseudo-differential operators. Practically, once you know the definition of pseudo-differential operator, you can extend everything to pseudo-differential operators once you prove it for differential operators.
So, but there'll be a certain class of function. I mean, when you go from homogeneous polynomials, now there's a certain class of functions that you will restrict to for the symbol of the corresponding pseudo-differential operator.
Symbol is even the very definition of pseudo-differential operator is complicated. You will have a sequence of homogeneous functions of different sigma lambda 1, sigma lambda 2, sigma lambda n of homogeneous functions with values in isomorphisms of E in F, okay, homomorphisms of E in F. You have a sequence like that, lambda 1, lambda 2, lambda n, decreasing. Something, the top lambda 1 will be called the degree of the operator. Lambda 1 will be called the degree of lambda 1 will be really, it can be any real number. It's not an integer. And then, of course, which is extended homogeneously. Of course, when you do the homogeneous extension, it need not even be continuous at the origin. You get operators which are not necessarily continuous at the origin. So,
the fractional powers and so on. Yeah.
And for such a sequence of sigma lambda, you can define an operator from you can only define an operator from the whole of sections of M, sections over the whole of M to sections over the whole of M. You can't do it for every open set. That becomes more complicated.
So would something like e to the Laplacian be?
Well, e to the, if you put e to the power minus t delta, they are
the heat kernel.
They are good kernel.
Yeah.
But with positive t, it doesn't even make sense. You have to be careful. It won't converge. It's a sigma.
So that's why. That won't be even over a compact.
If you're familiar with the singular integral operators, so-called singular integral operators, they are special cases of pseudo-differential operators. It's a pretty sophisticated business to talk about them. So my own knowledge is not very deep. So I dare not talk about it. So Atiyah and Singer invoke the theory, but however, it can be proved using fairly elementary facts about differential operators. The trade-off is that you have to use somewhat more sophisticated topology than what they use. The key step for proving this statement, this theorem, that analytic index of L and L prime are equal to their symbols, k-theoretic symbols are equal. One can use purely differential equations, and that too not very sophisticated things. But the key step is to construct a self-adjoint elliptic operator A of order 1 from the trivial bundle to the trivial bundle of rank 2 power n plus 1. You can construct this. And this construction is very closely follows the usual exterior differentiation on manifolds. If you think of exterior differentiation on manifolds, it goes from exterior P forms to exterior P plus 1 forms. And if you take its adjoint del, call it del, and that goes from P plus 1 form to P forms. And if you look at D plus del, that can be thought of as an elliptic operator from even forms to odd forms. That is one as is well known as an elliptic operator. And this kind of construction can be imitated in general to get on any manifold elliptic self-adjoint operator from a vector bundle. In fact, a vector bundle into itself, one can manage that. The construction essentially is suggested by Hodge theory, Theorem-Hodge theory. I think I'll skip this. I will not. Along the way, one also uses the fact that SL1 prime, SL2 prime are homotopy through symbols ST, all of the same order, homogeneous polynomial in the same order, then it is easy to show by using functional analysis that the analytic index is the same. But suppose the homotopy is not true things, but at either end, suppose the operator is the same, you approximate it using, you can approximate using by polynomials along the fiber by the standard method, except there is a parameter along the manifold. You can convolve with e power minus tx square and you make an approximation, but e power minus tx square on each fiber, t norm square, e power minus t norm square on each fiber separate. It varies with x, but you can do that convolution and get an approximation if you want. But the approximation will be an analytic function, and you can truncate the analytic function at any point of thing and get polynomial approximations. But polynomials are homogeneous, but what you can do is to replace, look at only on the sphere and make them all homogeneous by multiplying by suitable power of norm size square. By such a process, you can make them all homogeneous, and then the theorem will be proved. That's the kind of thing you can do without having recourse to pseudo-differential operators. Okay, then first, this is in the special case when the manifold is odd dimensional, it turns out that IAL is 0. The index is always 0. This is proved by using some very sophisticated business of the kernel of the heat kernel. You have an asymptotic expansion of the heat kernel along the diagonal on M cross M on the diagonal, and by using some sophisticated arguments, it can be done. But I can also use the kind of arguments I use to prove that the purely differential operator arguments, which I use to prove the dependence of analytic index only on the case symbol, to come to this conclusion also. I don't want to go into details; it's a bit messy, but it's a lot easier than the method using heat equations, kernel of the heat equation. But at some other point, I do have to talk about the heat of the kernel equation for something else. So I'll just explain you. The point is, yeah, in the case when the dimension is odd, first point to notice is that when you take the vector bundles, go up to E, the vector bundle Tm has a everywhere non-zero section, because Euler characteristic is 0. One knows that an odd dimensional manifold admits everywhere non-zero vector field. It's a standard theorem in topology. Because of that, you find that the two vector bundles, lifted vector bundles, are of course isomorphic on the sphere, and therefore even the original ones have to be isomorphic, because there is a section and you come back, the composite is identity, so the vector bundles themselves are isomorphic. That has to be used crucially in this. Now, I now come to so far I've talked only of the analytic index. Yes, please.
Is that last statement in the previous slide trivial in the sense like a self-adjoint operator always has the last statement in the previous slide? Is it trivial that self-adjoint operator has index 0? The fact that the symbol of this self-adjoint operator's index is 0, is it a trivial statement?
That's obvious. First of all, if you have a self-adjoint operator delta, the kernel of delta is same as, in general, for any elliptic operator D, kernel of D is isomorphic to the co-kernel of D star. When D equals D star, kernel and co-kernel become isomorphic.
Yes.
That's easy functional analysis. Now I'm going to talk next. I'm going to talk about the topological index of an elliptic operator. Now this here I think I'm going to assume a lot of statements from topology. Firstly, for any psi in Kxa, there is a cohomology class Ch psi called the Chern character of psi, which is an element of the direct sum of HQ, XYQ, when Q is even. XA it should be, it's not Y, XAQ. So, for every element you can associate a cohomology class, a mixed class, not a homogeneous class, not of particular degree, but sum of various things. It's called the Chern character. You can associate that, which is an element of the even cohomology, only the even degree terms are added up. It's a rational, you have to take rational coefficients. Churn classes, there are something called churn classes which are which have integral coefficients, but this churn character is a kind of polynomial in the churn classes with q coefficients, so you will only end up in having cohomology classes with coefficient q. In fact, psi to ch psi is a natural transform from the functor k to the functor h psi xq on the category of pairs. In other words, we have the following commutative diagram. Apply the k is itself as a functor, ch is a natural transformation, it goes from one functor to another functor. So this diagram is commutative is what a natural transformation means. That's all there is to it. Then there's another cohomology class called the tot class, which depends only on the manifold. It's a so-called characteristic class associated with tangent bundle of a manifold, TM. Actually, not the tangent bundle tensored with complex numbers. So it's a complex vector bundle which you have whose churn classes are actually called Pontryagin classes, and it's an element in the cohomology sigma 4k H4k MQ 4k degree cohomology, and it's a polynomial, and the element is a polynomial in Pontryagin classes of M. And the orientation on M determines for each P in M a generator 1P of the highest homology class HP, DPM, SPM. M is twice the dimension of M. This M should be 2M if M is the dimension of M. Moreover, there's a cohomology class called TOM M, if you like, THM, in HM, DM, SM, Z, such that it's called the TOM class, such that THM restricts to the generator in each fiber. Each fiber, if you look at DM, the fiber of DM is a disk, and the fiber of SM is a bounding sphere. And if you look at HM, disk modulo sphere, that is always Z. And what one wants is the TOM class has the property that when you restrict it, it becomes a generator of that DM modulo SM. Yeah, and the mapping which takes, well, the mapping, here is the situation. Here is H star, DM, SM, and H star M. What one can do is this. You have a projection like this. So, sorry, you have a projection like this. You can, now it turns out there is a special class TH here. TH is an element here. THM is what I called it. There is a special class here such that you take this element alpha here, take an element alpha here, cohomology being a contravariant functor, you get an element P star alpha here. And now there is a pairing H star DM cross H star DM SM into H star DM SM again. This so-called cup product. There is a pairing like this. So you put this, there is an element which is lying here, which is called, there's an element which I call TOM M there, TH M here. So what you do is you take this, you have this alpha here, pick up P star alpha, and you have TOM M here, and you can form the product, cup product here, and gets you into H star DM, into H star DM SM, this product. It turns out that so you get such a mapping from H star M to H star DM SM, which is forming the cup product of TOM M. This turns out to be an isomorphism. It's called the TOM isomorphism. Basically, what happens is this: if you have a cycle at the base, take the inverse image. It's like cycle cross a sphere, which is a higher dimensional cycle. Sphere itself is a cycle, and that, so it's a cycle in this space. And so that's how you define the, at the homology level, that's how you get a map. You dualize, you get cohomology, you have a map. Yeah. Now, the topological index is defined like this. You take the symbol of L, the k-theoretic symbol L, apply churn character to that, and to form the coproduct with the pullback of the TOM, pullback of TM to the disk bundle. Pullback of that to take that, form the coproduct, and then evaluate it on the fundamental class of D star M, SM star M. D star M, SM star, that pair should be simply D star SM star. There's no M there, that doesn't make sense. D star SM star is a manifold with boundary, and its boundary, that's a pair. And such a pair has a highest dimension cycle. So you can form the, evaluate this on this homology class, and as I said, this D star M, SM star Z, it's in this element, this should have been Z. Yeah, that element is a generator of this group, which is Z. The generator is determined by the orientation. So the whole thing is some cohomology class which you manufactured out of the geometric data and evaluated on the fundamental class of DM star SM. We can now state the index theorem. For a linear elliptic differential operator from a vector bundle E to another F on a compact manifold, analytic index is equal to topological index. The topological index is, looks pretty complicated in its definition, whereas the analytic index is much pleasanter to define. On the other hand, computing the analytic index is a tall order. If you have the topological data, the index is effectively computable. Okay, now, so the theorem is that the analytic index is equal to topological index. The way what Atiyah and Singer proved the theorem is to prove a number of properties which are common to both the topological index as well as the analytic index. Number of properties which are true. It's clear that the topological index depends only on the k-theoretic symbol by the very definition. The analytic index, we have to prove some things, but that is taken now. So to prove this, what they do is to prove both of them have a number of properties, and if you have if you have mapping from K star of DM SM into rational numbers to such homomorphisms which have this number of properties, they have to be equal. So topological index and the analytic index have all these properties, so they have to be equal is the proof. If they have all these properties, what are the properties they want? Firstly, okay, yeah, the one remarkable thing out of the index theorem is that the analytic index is obviously an integer, but the topological index is only a rational number because the churn character and so on involves polynomials with large denominators, big denominators. So you can only say it's a rational number. The remarkable thing is once you know that the analytic index is equal to the topological index is an integer. And in fact, this gave rise to some integrality theorems. There's something called the A hat genus, which essentially was introduced by Honorary. And that A hat genus turns out to be the index. It turns out it's a topological number which comes out. It turns out that the topological number is nothing but the topological index of the Dirac operator on a suitable spin manifold. And therefore, the A hat genus has to be an integer. Yeah, there are a number of properties of topological index and analytic index. So some of them we already talked about because it's obvious that both of them depend only on the k-theoretic symbol. That's the first property. And secondly, if you take product, so M and N are two manifolds, and you have an operator L on M and an operator L dash on N, you can form a kind of new operator out of L and L prime on M cross N, which you can call the product operator. And for that operator, once if the topological index and analytic index coincide for L and L prime, then it coincides for the product operator L prime on M cross N. So that's an important property both of them possess. So number of common properties, and using the common properties, what they did was to prove that it's enough to prove it for some special operators. Namely, one of the special operators you use is the you take the Theorem complex of differential forms and isolate take some of the even forms and some of the odd forms, and then you introduce the operator d plus del, where d is the exterior differential and del is the adjoint. D plus del, if you look at it, if you look at you can compute the analytic index because of Hodge theory. D plus del goes from even forms to odd forms, and Hodge theory tells you that the kernel of D plus del is precisely isomorphic to the even cohomology, and the co-kernel, again, which is the same thing as essentially kernel of del. It's the same. It is the co-kernel is the even odd cohomology, and the even cohomology minus odd cohomology, the ranks if you take is precisely the Euler characteristic, and that is the analytic index. And for the topological index, it turns out what you get is a certain differential form which comes out of the Gauss-Bonnet formula, and whose integral one knows is the Euler characteristic. So that proves for the special case, for the Theorem operator. You also have another operator introduced by Hitzebrew, who proved something about what is called signature of the manifold. It's a topological object. And he proved that the signature is got as the analytic index of a suitable operator. I mean, he didn't put it in the framework, but once you have this framework, you can interpret this theorem in this fashion. So what Atiyah and Singer did was to use an elaborate machine to reduce this to these two special cases, signature operator and the Theorem operator, Theorem Hodge operator. Now, I think I'll skip this. I've already told you that if the topological index as well as the analytic index are 0 in the case of odd dimensional manifold, and so for the odd dimensional manifold, the theorem is true. The index theorem is true. Now, for the index for the even dimensional case, we have to introduce a number of the problem has been reduced to first one reduces the problem to what are called twisted signature operators. This reduction to twisted signature operators is again comes from a deep theorem in topology. The twisted signature operators are a certain bunch of operators which sit on vector bundle into itself, and so on the manifold M. And as you vary the vector bundle, you get a number of twisted operators. Each of them gives you a symbol. So from E to the twisted symbol, you get a mapping which goes from K theory of the base map to the K theory of the BM-SM, the pair. Because it's an elliptic operator, you get an element. And this is an isomorphism after you tensor with Q. This is a fairly deep result in topology, but this has to be used. Use that, and so you can formulate everything as something about K theory on the manifold itself, and don't have to go to the BM-SM. And then there is one other theorem. So this twisted operators E, so you have a manifold M of dimension 2n, say, and the twisted operators are got like this, something like this. You take the d plus del of the Theorem complex, this goes from omega forms, even forms, to odd forms. But you can think of it as going from omega to omega itself, d plus del. Now, there is a star operator on forms. And if you look at star square is equal to -1 on odd forms and even forms. Now you can introduce another operator star prime, which is nothing but I power p into I power n minus p, where on p forms, then star square. Look at this, sorry, star. And then look at prime star square. This again is going to be, it's either, depending on the parity, it can be 1 or -1. That is, star square is 1 or -1. On even forms it's 1, and odd forms it's -1. Sorry. Yeah. Therefore, you look at the eigenspaces of star square. This star square commutes with d plus del because they are scalar operators after all. And so its eigenspaces will be stable. So you have eigenspace corresponding to I here, -1 here. So your eigenspaces -1 plus 1 are the eigenvalues here, and this here the eigenvalues for star square are I and -I. Separate the space into, decompose omega in a different way as eigenspaces corresponding to +1 and I, bunch them together, and take the eigenspaces corresponding to -1 and -I, bunch them together. So it's a different decomposition from instead of odd and even. And then you have still the operator d plus del goes from one to the other, one eigenspace to the other. This is the Hirzebruch twisted index operator. But if you have vector bundle addition, you can do all this with a tensor with E, and then you use a connection to, instead of exterior differentiation, you d omega given by the connection for forms with values in the vector bundle. And that is the twisted operator, twisted elliptic operator. So it is enough to prove the theorem for these operators. And for these operators, what is more, another thing that happens. Suppose, so now I'm doing things on the manifold M itself. M, and you have, suppose M prime are manifolds which together bound another manifold W. So this is W here, M and M prime bound this. And suppose you have vector bundle E on W. Restrict E to W, E to M, you get a vector bundle on M, and similarly on M prime. If you have such a situation, and you take the twisted, and introduce a connection there and twist it by that connection, delta gamma, on these eigenspaces. Let me call them W plus and W minus. W plus restricted to M. Look at this operator. And this is an elliptic operator. And similarly, you have d gamma plus del gamma on W plus restricted to M prime. Restricted to M prime. It turns out IA, the analytic index of this, is equal to the analytic index of d gamma plus delta gamma here. This is on M and this is on M prime. If the two together bound and there's a vector bundle which restricts to a certain bundle here and a certain bundle here, for those two corresponding bundles, the analytic index is the same. For this, the proof is quite delicate. I mean, what Atiyah and Singer use is some kind of theorems about solutions to the boundary value problem for so-called with quasi-boundary conditions. That's the kind of thing they use. There's another way of doing it using the heat equation, which I devised, but it's again too complicated to talk about. I also run out of time. So I think I will not say more about it. As you see, the general way of approaching the problem of the various steps are similar to what Atiyah and Singer did, though at every stage there are differences in the way the problem is attacked. Especially one of the last statement using the heat equation proof, I'm kind of proud of that proof. So that's it. That's all I want to say. It's a nice proof. Anyway, okay. Now some general remarks after this. I have some more slides to show, but I will not go into it. It has to do with proof. The whole thing, yeah.
For D plus D star,
yeah.
This last step reduces to Hodge theory, to the Hodge theorem, is it? Reduces to the Hodge theorem, is it?
Yeah.
And for the twisted,
the reduces the Hodge theorem.
Yeah.
And the case of for this other depreciation reduces to Hitzebrook's theorem about the signature.
Okay.
L genus being equal to signature.
Right.
L genus turns out to, L polynomial turns out to be the topological thing.
Okay.
And signature turns out to be you break up like this, and you look at kernels are always some part of homology. You're looking at some eigenvalues in the homology space, and you find all the, except for the middle dimension, you get pairing off of negative and positive.
Okay, okay.
And only in the middle dimension, the entire positives give you the kernel, and negatives give you the co-kernel.
Okay.
That's the way it works. Okay, now, some remarks. The theorem was the analytic index can be computable using purely topological methods is something conjectured by Gelfand. Gelfand conjectured it, but he didn't write down any formula and so on. And it was fairly sound reasoning, but not entirely satisfactory. Essentially said, if you homotop one symbol to another symbol, clearly the index doesn't change. So that was Gelfand's idea. And in fact, he supposed to remark when the theorem came out, big deal, I guessed it, this kind of thing. But that's very unfair, because the actual form that it is, the topological index involves character, Chern character and the Todd class and so on. It's not by any means obvious, but that was guessed at partly because of earlier theorems. Hitzebrook had proved his so-called Hitzebrook-Riemann rock, which again becomes a special case of this. And they looked at the kind of polynomial he was arriving at and integrating to get the result, and that was the cohomology class he was arriving at and so on. That's one thing. And also this Lichtenowig's, there's some connection with the Dirac operator, so they guessed that could be the index theorem, that its integral will come out of the index theorem, they guessed. All this put together, and they guessed at the actual form, the topological index, the formula for the topological index. And now, of course, there have been, as far as the fact that the index depends only on the k-theoretic symbol, also the so-called all new proofs start from that point. They assume that. For instance, the Atiyah Singer Patodi proof assumes that it is true that it depends only on the K star thing. It's after that. And then their method, it's essentially what was proposed by Singer originally. Atiyah bought Patodi, used this Singer method. Singer, there's a joint paper of Mikin and Singer in which they had a general conjecture about differential operators via the heat kernel, how to compute the analytic index using the heat kernel. Heat kernel, once you have a heat kernel, the rest of it is topology, so to speak. It's a differential geometry. What they proposed was to the heat kernel, by the heat kernel I mean you have the operator D, introduce D star D plus D star D is elliptic on one, D star is elliptic on the other, and both of them have heat equations, and you have the heat kernel, which has a asymptotic expansion along the diagonal. Heat kernel is something on M cross M, so you have asymptotic expansion along the diagonal in T. As T goes to 0, and it starts with some T power minus n by 2. In general, no, you should start with T power minus n by 2 and go n by D, where D is the order of the differential operator, and then n minus 1 by 2, n plus 1 by D, n plus 2 by D, and so on. That's the way it goes. I suppose something like that. Maybe I'm off by something. Anyway, and they looked at the starting terms T power minus 1 by 2, and if you look at it as the kernel, as the kernel of the operator E power minus T delta, then you can easily show that the kernel, what you are after, the analytic index is nothing but the operator, the trace of the operator, trace LL star minus trace L star L minus trace LL star. And for each of these, you use the heat equation expansion for the kernel and integrate it on the manifold and allow T to multiply by T per n by A or something and allow it to go to 0. Then you will get some expression. But that expression, what it exactly is, it's a big deal. I mean, it's not easy to. What Patodi did was he first dealt with the Theorem operator, where he proved that you get the Euler characteristic. Okay, you actually get the Gauss-Bonnet term. You have to integrate the Gauss-Bonnet term is what you find. That's what he proved, and that was quite a big accomplishment, no question about it. Then he went on to do it for more and more operators. Then he proved the Hitzelsberger-Mann-Drake theorem using that method, and everything depends on the fact there's a big cancellation in these asymptotic expansions. When you subtract one from the other, lots of cancellations takes place, and what remains is a nice expression which you can interpret in cohomological terms. That's what he did. And then he got, of course, invited after this performance. He was invited by Singer and Atiyah and so on. But I must say, before that, he sent his paper, the paper he wrote up and sent it to Singer. Singer did not respond. A few months after that, Narasimhan and Ramanan, who were abroad, came back from abroad, and they asked him to explain the proof to them. Then they made him recast the whole thing in better language, and it's that language which helped people to understand the theorem. Original Patodi's work was very difficult to understand for people. But between Narasimhan and Ramanan, they saw to it that he rewrote the whole thing, which is all his ideas, but in a form which is accessible to the general. It's only after that these people started getting excited over Patodi's work. The first manuscript which was sent to Singer did not get any response, but later the revised manuscript had immediate response. So that was the way it worked.
Which year was this?
This guy joined must be 71 or 72.
I see, okay.
No, Patodi is a remarkable guy. I mean, nobody knew he was working on this problem at the Tata Institute. I mean, he was a graduate student and was talking. Of course, he was recognized as an outstanding student. There's no question about that. But nobody knew that this guy is working on this Singer conjecture. One sudden day, he just produces this conjecture, produces this paper and says it's a theorem. So, and then of course, so after the point that it depends only on the K-theoretic symbol, there are several ways of attacking it. One is what was suggested by Atiyah. The point is suggested by Mekin and Singer, one way of attack on that. Because they wanted that formula which after the cancellation, the terms which you get are going to be differential forms. And the differential forms are really the substitutions of some certain polynomials, so in some polynomials of the curvature form of a suitable connection of a metric. That is what I have to prove, and which Patodi did with remarkable facility. And that is the way carried on and so on. And then instead of doing it, all this has to be done for signature operator, whatever operator. I mean, for the Atiyah Singer, you need to prove for all signature operators, which is what Atiyah Patodi did. But you can also have a different approach, and instead of that, use the Dirac operator. The Dirac operator also gives, if the manifold is a spin manifold, the Dirac operator also gives an isomorphism between K theory of the base and K theory of BM, DM, SM. And so you can use the Dirac operator. The Dirac operator again is, first you have the Dirac operator, some Dirac operator, and tensor with E. So you get twisted Dirac operators. So you'll have to prove the theorem for twisted Dirac operators. And a large bit of it was done by, what's her name now, I've forgotten already. Anyway, this French lady did it with the Dirac operator. And then there are also other takeoffs. I mean, there is the question of families of elliptic operators. And then there's a theorem which tells you how to, the families of elliptic operators, suppose the index then becomes a family of vector spaces, which means a vector bundle. So you have two vector bundles, but not necessarily vector bundle, because the dimension may change. Dimension of the kernel or co-kernel may change, though the difference doesn't change. Okay. So but still you can define, using those things, you can define a vector bundle on the base. The kernel at each point gives you a vector space, even though kernel minus co-kernel, that is constant, but dimension of kernel, dimension of co-kernel independently may not be constant. But nevertheless, you can manage to define a vector bundle out of that. So what you have done is for every element in the K theory at the top, you get an element of K theory in the image space. And there is something called the Grothendieck Riemann rock, which can be reformulated in this context, and that works. Okay. There have been other efforts, but I don't know too much about these things. As I said, there's a proof using probability methods, but once again, the heat equation plays an important role there. Probability method by Bismuth. Let's see. Sorry, I have taken 90 minutes.
Thank you very much, Professor Raghunathan, for taking us through this very seminal result and at least showing the contours of the proof. We'll look forward to the technical lectures. But before that, any questions either online or in person?
To make one comment that around mid-1960s, physicists actually also discovered some version of index. What I was saying is that around mid-1960s, physicists also were looking at phenomena similar, and they are called anomalous conservation laws. It's called the Adler-Bell-Jacob anomalies. And I just wanted to draw this parallel that in both the areas, mathematics and physics, something similar was being done actually. And in fact, there is a deep connection, and it's the same stuff actually.
I mean, yeah. Physics and maths have always had what they call a symbiotic relationship.
Yeah, in fact, it is from the Dirac operator. It's the same Dirac operator's properties that lead to this.
In fact, look at great physicists, even they are not rigorous mathematicians. The ideas are, I think, supremely helpful to mathematicians.
Thank you very much.
So this process of reduction, you said for the most general one, it could be reduced to one of these very simple cases. That is is it the statement that you said that it satisfies certain properties, and once you show that's all? So it sounds like a very powerful way in which you can reduce for a very general operator to...
Yeah, I mean, no. The point is, if you take for instance, if you go beyond operators of order 2, it's not clear how you can handle it.
Yeah, yeah.
That reduces to operators of order 2 is a big...
is a very big step, yeah. I mean, that seems very non-trivial that it... you could argue that, maybe.
Yeah, but the methods are very... I mean, I don't think the kind of methods used will be liked by physicists in general. I'm not sure. Even among mathematicians, there are followers of Grothendieck who like such methods, but there are others who don't.
No, my question was actually saying, is there a proof not use reduction in this case? Sorry? Is there a proof which does not use some kind of reduction in this case?
No. See, first of all, the whole thing is you're reducing to more than anything else, you're reducing to operators degree 2. To order 2 operators. And I don't think, if you don't, even the heat equation asymptotics are, when you go to higher dimensions, it becomes much more complicated. It becomes, it's much more messy. It's the same idea, but the way, the number of things you have to handle at the same time, it's a huge number. And so it becomes really messy, but people have managed it, they've done it. They've made an asymptotic expansion. Even for the pseudo-differential operators, there are asymptotic expansions, but it's you can follow what's going on step by step. but you don't get a global picture of what's happening. With operator order 2, you are in much greater comfort. And therefore, it's nice to reduce it to such operators. And for that, I'm particularly happy because it uses, the cobordism is one of the big tools. And being very fond of topology, I'm happy. And the Patodi's proof, for instance, is much more analysis in differential geometry. My proof, which I give, is much more accessible to topologists.
So you mentioned at that time the fact that the topological index is an integer was the proof was through the fact that it was equal to the analytic index. Yeah, the fact that the topological index is an integer when it is not manifestly one, the fact that it's actually an integer was because of this theorem that it's equal. Right. But is there since been independent understanding of that?
I don't think so. I don't think so. Some integrality results which topologists could prove by other means could also be proved by this method, by using suitable operators and so on. This idea of considering all objects of a certain kind and so on, this is something which started only with Hilbert. So it's a 20th century phenomenon. Before that, people were not looking at things in that fashion. You look at all objects satisfying something, and you want to prove properties about all of them, that kind of thing. It's very much a 20th century phenomenon.
And this construction of these K groups of DM, SM, that was due to Atiyah?
No, it's Atiyah Singer. The joint work.
No, there was a question.
No, I just want to know if your proof works for manifolds with boundary.
Sorry?
Does your proof work for manifolds with boundary?
No, yeah, that's another story. I have not really looked at it. It's possible to, even the statement for manifolds with boundary is something I have not yet really understood what it means. Okay, so I have to look at that before I can attempt to push my proof. And actually, I don't think I should be looking at it. It's a problem for a graduate student. Clearly.
For the audience members.
Is the index invariant on? Is this analytic index invariant on
invariant of what?
On the index is invariant, right, on compact manifolds?
He's asking if the analytic index for a differential operator are invariant for manifolds with boundary. Can that part of it be
first of all, the formulations will be different. You have to, for manifolds with boundary, you will have to impose boundary conditions with the operator. See, I'm not very familiar with that. If you impose certain boundary conditions, then the kernel and co-kernel will be finite. Then index can be defined. And the problem is to arrive at that index by some geometric method. I have not studied the papers relating to manifolds with boundary, so I don't really know. So,
but there are no concrete results on that?
There is a theorem for manifolds with boundary.
the APS?
There is a for manifolds with boundary and differential elliptic operators on it, and you're looking for solutions of a boundary value problem, that kind of thing.
Okay, if there are no further questions, nothing online, Bruno. So let's thank Professor Raghunathan again for a very enlightening lecture, and look forward to seeing you on Wednesday, 10:30 a.m.